Hi, this is Kemme. This is my 322 honors contract. Today we'll be talking about bending in two planes. But first we're going to start off with a little refresher in bending in one plane. So first, what is a moment? Moment is force times a distance. Then I is the moment of inertia. This is how difficult it is to bend something about that axis. So, given a rectangular beam with an x-axis and a vertical y-axis, given a height and a base, the formula for this for moment of inertia about the x-axis would be 1/12 base height cubed. And similarly, the moment of inertia about the y-axis formula is 1/12 height base cubed. Now moving on, our stress about the x-axis is determined as negative moment times y over I. Y here is the distance from the centroid. So along the centroid, bending stress equals 0. So some other terms. Y bar, this is our global centroid. And it's calculated by the formula y bar equals the sum of the areas times the arm over the sum of the areas. So, for an example, we have a T-shaped beam, like so, with dimensions of 8, 3, 10, and 2, given that everything is centered as it looks, with our origin in the corner here. This is our x-axis, our y-axis, with then y bar going this direction to right about here. To find that exact location, what we have is y bar equals 8 times 3 times 10 plus 1.5, because we're going up 10 and then to the center of the beam. So that's the splits the difference of this. Plus 2 times 10 times its distance of 5. So that's this beam up to the center 5. Over some of the areas, 8 times 3 plus 2 times 10. And when you calculate this out, we end up with 8.55. So then our distance from y is 0 here up would be 8.55. So then now look at the moment of inertia about the centroid. I centroid equals the sum of the segments of I of itself plus the area times distance of itself, 2 centroid squared. So, for that same example here, our I centroid would be equals 112 times 8 times 3 cubed plus 8 times 3 times, first we have our centroid location of 10 plus 1.5 minus 8.55 our global centroid, that whole quantity squared, plus, for the other beam, 1 over 12 times 2 times 10 cubed plus 2 times 10 times, this is between our centroid, 8.55 minus the centroid of the object itself, 5 squared. When this is calculated out, our I centroid ends up being 646 inches to the fourth. Now moving on to a full example of bending in one plane. Let's make it a little more complicated. So we have a cantilever beam. Apologize, that's supposed to be straight. The fixed end and a roller. And we're going to call this point A, this point B. The distance between here and the end is 20 inches, and the distance between the 2 points is 100 inches. At the end here we have a load of 2,000 pounds. I'll call this point D. And then 50 inches in from point A, we have another load of 2,000 pounds at point C. This beam has a cross section like this with dimensions of 1 inch, 3 inches, 1 inch, and 3 inches, with our standard coordinates of y going in this direction. So then now we find y bar to be 3 times 1 times 3.5 plus 1 times 3 times 1.5 over 3 times 1 plus 1 times 3. Find this to be, I find that to be 2.5 inches. So now we're going to calculate our moment of inertia. I'll leave this up here for you since it's a little longer. So we say I equals 112 times 3 times 1 cubed plus 3 times 1 times the quantity 1.5 minus 0.5 squared plus 112, 1 times 3 cubed plus 3 times 1 times 2.5 minus 1.5 squared. I find this to equal 8.5 inches to the 4th. So now when we do our moment and shear diagrams, we end up with two diagrams that will look like this. Alright, so at this point we have 600 pounds. Then at this we have minus 1,400 pounds, and then jumps back up to 2,000 pounds. When we do all the force bounds, just move through this quicker. Same thing with the moment diagram, where we have the moment go up, come back down, and then back up. X. So this here is 30,000 pound-inches, and this is negative 40,000 pound-inches. So then with this information here, now we can find our maximum compression and tensile forces. So sigma C, so the top of the beam, we have our moment, negative 30,000, times our Y, 1.5, over our I, 8.5. This gives us a value of negative 5.294 psi. So remember, it's negative m y over I. And so now let's go through all these real quick. So then sigma C bottom equals negative 30,000 times negative 2.5 over 8.5, and that gives us a value of 8,824 psi. And then we have sigma B top and sigma B bottom. And so now we are using our other moment. So you have negative 40,000 times 1.5 over 8.5, which then equals 7059 psi. And then also have negative 40,000 times negative 2.5 over 8.5, and then this equals negative 11765 psi. So now we come back and look through these, and we find that we have this one here. It's our maximum tensile, because it's the maximum positive force or stress. And then we have here, we have our maximum compression, as it is the technically smallest but largest negative value that we have. So now that we have gone over bending in one plane, now we'll do bending in two planes. So, given another one of these T-beams, with axes like so, with a neutral plane that goes along the length of the beam, you'll have two moments. You'll have one along this axis, and then you'll have one along this axis. And that's where this one here, using the right hand rule, would give us a force that is trying to bend the beam this way, whereas this one is trying to bend the beam up. And that's given a force at the top here, pushing down. So just a little bit more terminology of what we have to look for when looking at the cross-section of a beam. We have, keep this black for a second. We have our z-axis, and then our y-axis, positive z and positive y, and then our x-axis is coming out this direction. So then now when we are looking at a moment this direction here, we have this angle from positive z to positive y, it's theta, with then moment of my in this direction, and then we have a moment of mz in that direction. So just need to remember that theta is always measured from positive z to positive y. And so now we have two planes that we're looking at. We have sigma equals negative mz y over I plus my z over I. I apologize. These are iz and iy. Iy is the moment of inertia with respect to the y-axis. It's the neutral axis. So y-axis is the neutral axis. Iz, same idea, except this time it is the z-axis. It's a neutral axis. And then z has the maximum moment of inertia by convention, and y is the minimum. So mz becomes our normal moment times cosine theta, and my is m sine theta. Standard geometry. Then along the neutral axis, sigma equals 0. So going to how this actually looks based on the distribution, we have a normal beam. We would have a distribution that looks something like this. So we have our neutral axis go across this point here with all of our forces going in this direction above and all of our forces pulling out this way below. So then we have here a couple more small calculations of y equals my iz. Sorry for using that notation. Over M, Y, I, Y, and then Z equals tangent theta, I, Z, I, Y. And then when we're looking horizontally, assuming this is the axis, the angle between the neutral axis here and normal axis, this angle is alpha. So then tangent of alpha equals IZ over IY tangent theta. And theta does not equal alpha. Remember, theta is our angle between the z-axis and the normal y-axis, where we have our normal moment before we break it into any of its components. So now we have an example. So when we have this here, this is our example. We're going to have normal beam, nothing fancy, with our positive y and our positive z axes. Our moment is in this direction, resulting in a positive mz and a negative my component. Our points are B, C, E, and D at the corners. Our angle from the z-axis to the moment is 53.1 degrees. But remember, normally when we have to do any calculation, this is measured from positive z to positive y. So I'll be going this direction. You have to remember that this is negative then for any calculations we use. The axes are centered with distances of 0.01 from the edge to the center this direction and 0.02 from this edge to the center. So we calculate our resultant forces, or resultant moment, sorry. My is negative 9.6 kilonewtons per meter, and then our mz is m cosine 53.1, which results in 7.2 kilonewtons per meter. Iy is 1/12, 0.4 times 0.2 cubed, which then results in 0.02667 times 10 to the third meters to the fourth. Similarly with Iz, we have 1.067 times 10 to the third meters to the fourth. And that's just our standard moment of inertia equations. So remember now when we find our stresses, positive stress is tensile and negative stress is compressive. So sigma b, calculate here, we have our negative mz times y over Iz plus my z over Iy. That gives us 2.25 megapascals. So when we look at the drawing, we have our mz, this is our y location here. So to get to point B from the center, we go positive 0.2 in the y, and we have to go negative 0.1 in the z. So then for C, it's the same calculation, it's just this is now positive because instead of going backwards to B, we now go forwards in the positive z direction towards C. Same idea for D and E, where now we're going negative in the y to E, negative in the y to D, but negative in the z to E, and positive in the z to D. We end up with these values here of sigma b is 2.25 megapascals, sigma c is negative 4.95 megapascals, sigma d is negative 2.25 megapascals, and sigma e is 4.95 megapascals. Now, using the formula we learned earlier to find alpha, which is the angle of the neutral axis, which is Iz over Iy times the tangent theta. So remember we had negative because normally our theta is measured from positive z to positive y. So that'd be all the way around, or a negative angle. And that gives us an angle of negative 79.4 degrees. So looking from the top of the beam, we'd look at something like this. We'd have our positive y, positive z, our moment with that angle theta, and then a neutral axis here with that angle alpha. For another problem, it's the same idea. You just have to calculate your i's, your moments, and then find your sigma by plugging into the standard equation. When you're done, plug it into your tangent alpha equation, find the neutral axis, and you're done. Thank you.